Hello everyone and welcome to today's presentation titled HoloPair, Securing Shared Augmented Reality Using Microsoft HoloLens. My name is Josh Huffman from Georgia Tech, and I will be presenting the research that was performed by the individuals that you see listed here from the University of Oxford and the University of Zagreb. So let's go ahead and get started. The main purpose of this research was to develop a means to securely connect multiple augmented reality devices. Obviously, not securely connecting these devices leaves the platform open to a series of cyber attacks, and specifically man-in-the-middle attacks that we'll be discussing in this research. And at the time of this research, there were no solutions that existed for securely pairing AR devices. So the researchers developed their own prototype that they named HoloPair. And they also performed a user study using 22 participants. So we'll be getting into all the details of their prototype and also the results from the study. So the hardware that was used for this research was the Microsoft HoloLens, which is pictured here on the right. And it is a self-contained head-mounted computing unit. And by self-contained, we mean that the device does not need to be connected to any sort of external computers to work. It's completely untethered and does all the computing on the headset itself. It runs on Windows Mixed Reality platform, and it performs real-time position tracking without the need for any sort of external sensors or markers. So as the user walks around within their environment, it's automatically tracking and creating a mapping of the interior of the building that they're in. So this device allows the rendering of realistic 3D content that Microsoft calls holograms that appears anchored down to the real world. So for instance, a user could place a 3D object in a specific room in their house. They could then leave that room and come back, and that 3D object will still be there, anchored in the same place that they put it. The HoloLens uses gestures as its primary way to interact with the device, so using things such as a pointing motion or making a sort of clicking gesture with your fingers to do various things on the device. The HoloLens also is capable of co-located collaboration, meaning that multiple users can have a HoloLens on and they can be looking at and interacting with the same virtual content within the same room. And so this feature is kind of at the heart of what this research is. So we'll be getting more into that. The challenge here is that the existing secure device pairing protocols are not really relevant for AR headsets. The AR platform in itself is sort of an atypical case. So AR pairing requires two users and not just simply one user on two devices. The devices are meant to be worn by a user for the duration of a workday, and they can only view the output that they're seeing on their own device. We must also assume that an adversary is able to eavesdrop on the out-of-band communication, so things like the front-facing cameras on the HoloLens. And in a typical adversary model, the concern is usually only the wireless channel that the devices are connected to. So this AR platform and using AR headsets there's some different issues and things that are not typical. So the diagram here is showing the basic system model, and just to give you kind of an idea of the scenario that we're talking about here. So you have two users here, user A and user B, each with a HoloLens on, and those HoloLens devices are connected via the same wireless network. And we're going to assume for this research that that wireless network is also controlled by the adversary. And then you can see that the users are communicating over the visual channel. They're both looking at some sort of virtual content and then both interacting with it. So the adversary's goal here is to use their own device, whatever that may be, to prevent user A and user B from establishing a secure connection. And they're going to do this by means of a man-in-the-middle attack. So we're going to assume also that the adversary is co-located with the two users. So they're close enough by to be able to perform this sort of attack. And we're going to assume that they're able to eavesdrop on the visual channel, but they're not able to actually see the holograms that the individual headsets are generating. It's also worth noting that for this particular research, they did not consider any sort of denial of service attack, so not focused on that for this. So there were three main design goals here for this research. For security, the attacker must have a low chance of success with the man-in-the-middle attack, and users should be able to detect a majority of the time when an attack is actually occurring. And then from a usability standpoint, the user must not be required to remove their headset, and whatever interaction is required of the user should be rather brief. And then for the hardware requirements, they wanted to make sure that there weren't any additional capabilities or add-ons that were needed to use this pairing protocol. Nothing that the headset doesn't already provide, essentially. And it should be low computation, low memory, and energy consumption as well. So here we see a few pictures of their prototype in action. The top picture, we're seeing user A and user B, and that is from the view that is outside of the AR view. That's just to show you, kind of how far they are away from each other. And then the bottom two pictures are what user A and user B are actually seeing in their devices. You can see that they're seeing this shared shape, essentially. So what's happening here from a high level is that there's going to be an exchange of public keys over the insecure wireless channel, and the users are going to confirm the authenticity of the exchange keys using the visual channel, and that's done by means of gestures. And in this case, they're basically tracing a shape. So you can see the bottom left picture there, user B is using her finger to trace the shape starting at number 1 and going all the way to number 6 there. Here we see a swim lane diagram of the pairing protocol. And there's basically 3 main steps in the pairing protocol. So first, as we mentioned before, there's the public key exchange. And then there is the weak hash commitment. And from the user standpoint, essentially all they have to do is user B has to wave at user A, and then user A confirms that the other user has waved. And then the third step there is the shared secret confirmation, and that's where they're doing the more complex gesture of tracing the shape following the number scheme. So from a security standpoint, in order for the adversary to perform a successful eavesdrop, essentially they have to force the users to agree upon a false set of public keys. And they must ensure that the shared secret confirmation finishes successfully, and that can only happen if the weak hashes that are computed by both devices are found to be equal. So they must commit the same value k from the weak hash commitment step before discovering the actual value of k in the shared secret confirmation step. So that's all to say that in order for an adversary to perform a successful attack, they really have no other alternative but to randomly guess the replacements for the public keys that would end up with the same hashes on both devices, essentially. So user inattentiveness is another security concern that the researchers looked at. And basically they found that the highest probability of a successful attack would result when a user accepts the gesture inputted by the other user without actually confirming that the gesture was correct. Essentially, when, say, user B is tracing the shape with their finger, the other user is supposed to be watching and ensuring that the shape that's being traced by the other user lines up with what they're seeing. And if it does not, then you know that there's some sort of tampering that has taken place. But sometimes users get in a hurry and they just go ahead and accept that the gesture was correct without it actually being correct. Or they simply just, were clicking through quickly before the gesture even occurred. So the researcher performed a user study in order to give an estimate on the user's ability to detect an attack. And we'll see the results of that here in a minute. So a little bit more about their prototype. It was written in C# and it uses the Unity framework. And everything is open and available. The source code is available on GitHub. For the network and device discovery, they used Unity's high-level networking API. For the cryptographic function, they use Microsoft 2048-bit RSA PKCS1 for the asymmetric cryptography and 256-bit SHA-2 for the hashing. And then for constructing the shared hologram from the weak hash, the shapes that were representing the weak hashes are generated by extracting bits from the full hash to define n coordinates that define them. And then for each of these n points that make up the shape, they extract binary bits to generate one of 10 x coordinates and one of 10 y coordinates. And then in order for multiple devices to show the same content, the devices need to agree upon a shared coordinate system. And so they are using the Holo toolkits, which is provided by Microsoft. They're using the world anchoring feature in order to achieve this. For positioning the shared holograms, essentially, as you saw in the pictures, each user sees the hologram in front of them. And it's on a line between the two users, and it's about 1.5 meters from user B is where it starts, and then it gradually moves closer to user B over the course of 3 seconds, and then it stops at a final distance of 0.85 meters. And the reason that they do it this way is the HoloLens has a rather narrow field of view. So they want to start with the hologram far enough away from the user so that they can see the entirety of that hologram. And then they slowly bring it closer so that it's close enough for the user to actually interact with and trace with their finger. So then for the confirmation of success or an abort, user A confirms the observed gesture is correct by simply looking at the other user and performing a click gesture with their fingers. And if the observed gesture does not line up with what they're seeing, then the user should say the voice command abort, and that ends the pairing protocol. So from a user experience, the instructions were very straightforward for the users. So user A, we're told that once you see user B wave, you look back at them and you do the click gesture. And then you're going to observe as they trace the shape with their finger. And if it appears correct, you use the click gesture again. Otherwise, you say abort out loud. And then the instructions for user B was to simply wave at user A. And then once you see the shape appear, you're going to move your finger along the shape starting from number 1. So getting into the user study, there were 22 participants, 14 female, 18 male, from the ages of 21 to 33. And they were briefed on the purpose of the research, and they were asked to perform the pairing steps several times. And then they were told that the researchers may attempt to do a cyber attack randomly during some of the attempts. So each participant played the role of user A and user B at least 10 times, so they switched roles. So the independent variables here in the study, the attack simulation. So to evaluate the user's ability to detect an attack, in 20% of the pairing attempts, they did a man in the middle, or at least they simulated a man in the middle attack by showing the users differing shapes. And then for the N shape complexity, to evaluate the impact of the complexity of the shared secret confirmation step on the dependent variables, which is total time and success rates, the value of N, which corresponds to the number of shape segments, was randomly chosen between 4, 6, and 8. So the data collected here. So there were 230 total pairing attempts, 44 of which they simulated an attack. And then for each of those pairing attempts, they recorded the timestamps at which the users reached each step of the protocol. And then they recorded whether the pairing attempt was successful, either by detecting an attack or correctly exchanging the shared secret. So the chart here shows the results of the pairing time. As we can see, it's a median time for the users to pair was between about 8 and 9 seconds, with 80% of successful pairing attempts finishing in less than 13 seconds. Also, when a simulated attack was detected by the user, the average pairing time actually did increase slightly, but the researchers noted that this was largely due to the fact that when the users were seeing differing shapes, they would actually trace the shape a couple times before actually deciding to abort. And also, some users had a problem with their voices being recognized when they said abort, so they'd have to say it multiple times, and that of course increased the pairing time as well. So with the complexity of N, as N was changing from 4 up to 8, the average pairing time actually only slightly increases. And what they're saying here is that this indicates that the total time spent performing the gesture does not depend on the complexity of that particular shape as much as it does other behaviors such as the user waiting around or trying to make a decision or doing some sort of clicking gesture. So 91% of the simulated attacks were actually detected by participants. 98% of pairing attempts were successful with no simulated attack, and there were 4 false aborts. They also looked at the learning effects. So here we see that the mean pairing time reduced as users repeated the pairing protocol multiple times. So on their first attempt, it took about 11 seconds for them to complete the pairing. And then by their 10th time, we see that it only took about 9 seconds. So they got better as they went. From a usability standpoint, after the participants performed the multiple pairings, they were asked to complete what's called a system usability scale, or a SUS. And this is a general tool for evaluating the usability of various systems. It consists of 10 questions that users grade on a Likert scale, where 1 means strongly disagree and 5 means strongly agree. And overall, the responses show a high average SUS score of 86.4. And here we show the list of questions that were asked just for completeness sake. So finally, we have the performance of the prototype. The maximal increase in the GPU, RAM, and CPU load was below 15% of their max amounts, and the total application size was 130 megabytes. And so we see that they have achieved a low overall impact on the HoloLens device with their prototype. So in conclusion, the HoloPair was shown to be a secure and usable protocol and system for pairing AR headsets. The participants had little or no experience using AR headsets and were able to achieve a high rate of detecting a simulated attack or successful pairing when no attack was present. The system was highly usable, as made evident by the short pairing times and the high scores on the usability questions. And it was low computational requirements with this prototype. So as shared collaboration in AR becomes more and more commonplace, obviously securing these devices will become even more important. And so the HoloPair prototype and protocol is under consideration by Microsoft to be included in the official HoloLens toolkit. So that concludes the presentation today. To my fellow students, if you have any questions, feel free to ask on the Piazza forum. Thank you.